is identities part 2. I was a little hesitant to start identities part 2, but it really only introduces the restriction idea, and we hinted at that in the last lesson. We have problems in the denominator when we generate zeros, and we're going to take a look at some of those suggestions and restrictions on domains. So turn the page over with me. So the identity, the policeman's down here at the bottom, the identity that sine x is equal to tan x cosine x is true if I consider that cosine x cannot be 0, which would happen at pi over 2 and jumps of pi. So some suggestions. All tangent, cotangent, secant, and cosecant identities or equations have non-permissible values because you have denominators. When your denominator is equal to 0, the graph doesn't exist, the function doesn't exist, you cannot use it. Those non-permissible values are sometimes called restrictions of the identity. And in many of the examples, the restrictions are the solutions to when sine x equals 0 or cosine x equals 0. Remember, sine x is equal to 0 at pi's, 0, pi, 1 pi, 2 pi, 3 pi, 4 pi. And cosine x is equal to 0 at multiples of 90 degrees plus or minus pi. And those are things we've already worked with. So this lesson seeks to deal with identities that are a little bit more complex. So we had fun dealing with or finding the Pythagorean identities, but now we're going to put them to use. Hints in proving an identity. Always start with the more complex side. If possible, use a reciprocal quotient or Pythagorean identity. Look for those opportunities. If necessary, change all trig ratios to sines and or cosines. Look for factoring. If there is a sum or a difference, look for opportunities to combine as a single fraction. So ladies and gentlemen, this takes practice. It takes a willingness to occasionally make mistakes. And I'm going to try and record and produce as I go. So 1 over cosine x minus cosine x. Well, as far as I can tell, that's written in as many cosines as possible on the left-hand side. Not sure what I can do to simplify that. 1 over cosine x minus cosine x. Not sure how I can simplify that. Oh, it's a fraction. So because it's a fraction, I want to try and make a common denominator. So common denominator, multiply cosine x, multiply by cosine x, top and bottom. So then I get 1 minus cosine squared x over cosine x. And 1 minus cosine squared x is actually from my Pythagorean identity. 1 minus cosine squared x is actually equal to sine squared x. So this is sine squared x over cosine x. And I kind of know what I have to build. I have to build sine x times tan x. Well, if I can factor that sine x out, I'll be left with, so I'll just shift to the left here. I factor a sine x out, and I'm left with sine x over cosine x, which is in fact equal to sine x times tan x. I've made my left side look like my right side, so I get to say left side equals right side. Put an equal sign in between it. You can graph it if you want. You can plug and play for pi over 3. See if that works. Sorry, I was so excited to prove the identity. I actually did the C part first. So I applied our identity applications already. You can plug in pi over 3 and make sure that what comes out of the left-hand side is equal to what comes out of the right-hand side. I'll leave that for you to try out. So plug and play pi over 3. When you're looking for these, for these possibilities to plug and play, try to pick a weird degree like 20 or 27. Don't pick 0. Don't necessarily pick 90s or 180s because that runs into troubles. Do I have any restrictions on this identity? Let's take a look. So here's the restriction for this one. Cosine x cannot be equal to 0. It's living in the denominator. That's a problem. Cosine x is equal to 0 when x is pi over 2 or any multiple of pi. So I've got my restrictions. So again, I'll challenge myself to do it in the same way. Can I simply attack this? I'm going to attack the most complicated side, which is the left-hand side. And the first one is my ability to factor out a sine. So I can factor a sine x out, and then I'm left with cosine squared x plus sine squared x. Well, that's really good. That's a straight-up Pythagorean identity. That's sine x times 1, which is just sine x. What's living on the other side? On the other side, I have 1 over cosecant x. And pardon me. 1 over cosecant x is actually equal to sine x by definition. So I can get on the right-hand side. So I simply get to say, hey, my left-hand side equals my right-hand side. And we've got one more left to do, or two. Let's turn the page over. So I'm just studying this one to figure out how I should begin. I'm going to begin by writing everything in terms of sine and cosine, I think. So split my paper in half and try to write in terms of sine and cosine. Plus oh, all right, so I've tried to fix my sound. In the top, I have to find a common denominator, and this might actually take a little bit more room, so I'm going to get rid of this line for right now. So common denominator, I'm going to put this, pardon me, going to put sine A over cos A. So I have to multiply by cos A on the top. So that's cos A sine A plus sine A all over a single numerator, denominator, pardon me, of cos A, divide by 1 plus cosine A. And I'm going to shift up and over here. So in the numerator of the numerator, I can factor out a sine A. So that's great. I'm left with sine A times cos A plus 1 over cos A, divide by 1 plus cos A, 1 plus cos A, which now I share a numerator and a denominator position, which I can cancel out. And I'm left with sine A over cos A, which is by definition tan A. So I've been able to take my left-hand side and make it equal to tan A. And when I look at my right-hand side, I know and you know that 1 over cotan A is equal to tan A. So I get to say that my left-hand side is equal to my right-hand side. When am I going to have troubles? I'm going to have troubles when 1 plus cosine A equals 0. So that's when cosine A equals -1. I'm also going to have troubles when 1 over cotan A, because that's living in a denominator, I'm going to have troubles with that one when cosine A is equal to 0. And we know when that happens. A cannot equal pi over 2 plus n pi. So you can take a look at what that graph might look like and where the non-permissible values come in. I want to try one more proving the identity, and then we get to play with the art and science of identities today, and probably a little bit of Monday's class. We're pushing hard. I know that. I appreciate that. What can I do with the left-hand side? Secant squared x over secant squared x minus 1. Well, secant squared x minus 1 is actually an identity or a manufacture of an identity. So that's the first thing I'm going to do is I'm going to replace secant squared x minus 1 with tan squared x. And now my only option is to convert to sines and cosines. So secant squared is 1 over cosine squared x, and tan squared is sine squared x over cosine squared x. And taking a look at multiplying by the reciprocal, cos squared x, sine squared x, cos squared x. It takes a while to get this detective work down. Sine squared x, cos squared x cancels in the denominator. In the numerator, some of it also cancels, and I'm left with 1 over sine squared x, which I actually recognize to be equal to CSC squared x. So I've actually made my left-hand side equal my right-hand side. And that's considered to have proven the identity. So that's it for our work for identities. We keep adding complexities to it, so you can imagine that Monday becomes a little bit more complex. So check this out today. Have fun.